So today we're going to talk about green chemistry and especially the 12 principles in system thinking. So who's never heard about the 12 principles of green chemistry before? Okay, good. So we're going to learn some stuff today. So before so a lot of things happened around 25 years ago in 25 years ago in the year in the 90s, where really people started to ask themselves questions about this, how to make chemistry better. And at the time, people thought that hazard should be managed or could be managed. Pollution can be controlled if we do engineering properly. High reactivity of reagents and substrates can lower reaction time and energy cost. Long-term durability of molecules and materials are a good thing. Organic solvents are always required for chemical transformations. Toxicity and function are always linked. We discussed about this yesterday. You remember function is important and toxicity sometimes comes in a way. And at the time, a lot of people thought, yeah, you have to accept the toxicity if you want the function. Environmental issues, it's simply a question of money. We can fix them by doing some remediation. And our responsibility as chemists is just to comply with the law that exists, and that's it. So this was the mindset initially that people had in that time. And of course, gradually people realized that this didn't make sense. And some of the issues that we've discussed since the beginning of this of this workshop, talking about accidents, talking about environmental pollution, really didn't make sense with this mindset. And so what was realized is that the hazard actually is a design flaw. We discussed about this yesterday, and it should be addressed by making a conscious design. Pollution can and should be avoided, and waste should be used as resources. Nature does chemistry much better than us. And in fact, it does it because it does it at the right time and the right place. And it uses benign materials. Persistence of a material beyond its useful life is bad and should be avoided. Benign solvents and solventless system actually should be the rule. We should not have to do everything in organic solvents that are toxic and will go easily to the environment. Toxicity can be minimal, while function will be there and potentially even enhanced. And we should invent green chemistry, right? Because it should solve these environmental and health issues that we're talking about. And chemists and engineers can work together for global sustainability. So that's the principles that have led these two gentlemen, Paul Anastas and John Warner, at the during this decade in the 90s to really think hard and say, how can we make how can we make chemistry better, and how can we make green chemistry? So they wrote this book called Green Chemistry Theory and Practice, which has been the reference for us since then. And this is a book so we celebrated the 25th anniversary of this book last year, which was really a nice event. And really trying to reflect upon all the influence that this book had on all our field by really bringing about these concepts of we need to do better. We need to do better. We need to prioritize human health and the environment, and we need to have better design to do that. So the concept was fulfill the function and negotiate the hazard. The hazard was not a good idea. We need to erase that and stop doing this, so that we could fulfill the function on the one end and eliminate the hazard at the same time. Of course, it's harder to do it than to say it, right? So we're like 25 years ago plus after this book, and we're still struggling to do some of this. But there's been progress as well. There's been some really good things that have happened, and we need to continue to try to make this thing true, create function while eliminating hazard. But I think this direction is really useful for us in understanding all of these questions. And very similar to what we saw yesterday, initially you have the cost, the safety, and performance that are seen in a completely disconnected way, whereas green chemistry is really trying to bring all of these concepts together, so safe and also being being cost appropriate or having a cost that we can afford. So this idea is really that what we need to do is to do benign by design. So from the beginning of the design experiment, at the same time as considering the function. And this is this little chart that we saw yesterday already about how we make this new design, which is really integrating all of these thought process we need to go through in order to make a truly green material. So if we are intentional about what we do, we can be better at making benign the truth and the reality. Sorry. So in this book that was published in 1998, there's an important component that has really lasted. And this, I think, is the best known fact about this book. And it's called the 12 Principles of Green Chemistry. So in this 12 Principles of Green Chemistry, what John and Paul said is that these are 12 ideas, 12 points that you can check when you are doing your design of a material and check if you are doing a good thing. So it's really about design deep down. So these 12 points are waste prevention, atom economy, less hazardous chemical synthesis, designing safer chemicals, safer solvents and auxiliary, design for energy efficiency, use of renewable feedstock, reduced derivative catalysis, design for degradation, real-time pollution prevention, and safer chemistry for accident prevention. Okay, I read all of that and you have no idea what I said because it's too much information, right? So what we're going to do in the next few slides is I'm going to go through each of them and try to explain what they mean, right? But some of the terms, you recognize them. For instance, the notion of degradation or the notion of renewable. So these are things that you know. Less hazardous, this is understandable, and accident prevention. So there's already some ideas that we have, but we're going to go into the detail of each of them. So that's a little wheel that, again, contains the 12 principles, and we're going to go around the wheel one by one. So the first one is called waste prevention. So it's a very simple idea. In this principle, what we do is we say, okay, how can we prevent waste from even happening? Because when waste is there, we need to treat it, we need to clean it up, we need to dispose of it, and all of that actually has a cost. We discussed a little bit about this during the keynote yesterday when we talked about crustacean waste that is coming with actually consequences. So the concept of waste is actually really interesting. It's entirely human, and I would say entirely human since the beginning of history, I would say. In ancient times, or still with indigenous people, the notion of waste as well does not exist. Indigenous people, they will take they will kill an animal and they will take everything of this animal, from the fur to the skin to the bones to the meat, of course, that they eat. Every part of the animal will be used for something. So waste is something that nature doesn't do, and that humans started to do at some point in their history when they got lazy, frankly. Like, they could afford to throw things away because they had enough resources to go about their lives. So, but of course, we now know at the scale that we're at, the number of humans on the planet and so on, and all the pressure we impose on the planet, we know that we have to change that. So what we should do is preventing residues in chemistry, and we can really do this from the design of the chemistry itself, really starting to think, okay, how am I doing my reaction? How am I doing my workup to really lower the production of the waste to begin with? So most of the waste chemistry is produced when you do your reaction because it's inefficient, or after the reaction because you're doing your cleanup, your workup, and during the workup, waste is also created. So if you have better working condition, if you optimize your reaction for minimizing waste, that's a good point. You can avoid purification steps by, for instance, having fewer steps or not, or having steps that don't require purification because your reaction is very pure at the end. All of these points are good. You can apply the least wasteful starting materials as well. So again, this is a question of design. How do I pick my starting materials? The second point is called atom economy. So that's a concept that's a little bit central to chemistry, in a sense that it's really this idea of how, when you do chemistry, you have starting materials on the one end and reagents and the products and residues on the other side. And what atom economy says is that you want to make sure you end up in your product and not in your residue. So here are two examples. I have this reaction here, two reactions, two identical reactions of an oxidation of an alcohol here. You have on the one end a reaction where the oxidant is this complex mixture of chromium oxide and some sulfuric acid. You will mix them together, and at the end, look at all of the atoms that are not in the product. This is not atom economy, right? We don't have a good economy of atom, if you see what I mean. Whereas in this process where we use a catalyst and oxygen as your oxidant, you only have as a side product water. So now most of the atoms go in the product, very few go in the residue, and that's a good atom economy. So that's the second principle. The third principle is to think about doing less hazardous chemical synthesis to begin with. So we're going to segue into something a little bit different than pure synthetic chemistry here. We're going to talk a bit about electrochemistry. And this is an electrochemical reaction where this is for the production of chlorine, which used to happen with using mercury cells in order to do the transformation. So that you can transform salt into chlorine on the one end and sodium hydroxide on the other end, which are needed, for instance, for the paper making industry. So this is the legacy chemistry. It uses actually mercury in the system. So this is really bad if there's leak or incidents during operating the machine. Of course, we're releasing a toxic compound. This is very bad. And this is an alternative for the chloroalkali process, in which you can do this chemistry with different electrodes, which now do not contain anything toxic. So this is an example of going from toxic to less toxic and thus less hazardous chemical synthesis. So design for safer chemicals, that is zooming now on the product that you make, right? So you've made your reactions, you made your product ends up in something that we all have, like the glass in front of you, the material that makes the napkins that you have. What you want is that these things are safe. You don't want to have this material here to exude some toxic compound so that when you touch it, you get contaminated. That's bad. So some examples of that are the phthalate plasticizers. Yes, sorry. Oh, thank you. Phthalate plasticizers, they're molecules that have this formula here, are super important in the plastic industry because they help make the plastic malleable enough that you can form things with it. So, if you want to form, so PVC, for instance, is plastic that is used for making a lot of things like tubes here, and they contain a ton of phthalates because PVC is difficult to form. PVC typically contains up to 40% in weight of other things than PVC itself. So it's something really, really serious. And people discovered after using them and everything that phthalate actually are hormone disruptors. So it can interact with your body and actually change the chemistry of enzymes in your body to do things like changing interacting with your reproductive organs, for instance. So, of course, when toys contain phthalates, it's really scary because babies can chew on them, and it could have adverse effect on their development and especially their sexual organ development. So this is an example of a plasticizer that is made from azelaic acid. It is actually biodegradable, which phthalates are not. And also it is much safer and it doesn't act as an endocrine disruptor. And that's an example of a good alternative that you could use in green chemistry for designing safer chemicals. The fifth one, it's over here. It's using safer solvents. So solvents or reagents, they are molecules that we use to help the reaction happen. They don't end up in a product, but they're really important for the process. They're linked to the production of waste, so it's also linked to another principle here. And this is an example of a list of solvents. This is a solvent guide that was put together by GSK, which is showing if a solvent is actually safe or toxic, to really guide people towards eliminating the use of the solvents that belong to this category here. And in the field of green chemistry, people invented a lot of solutions to that problem by, for instance, inventing new types of solvents, such as ionic liquids or supercritical CO2, or also creating reactions in a solvent-less environment. And we saw that yesterday when we spoke about mechanochemistry. The sixth point is the design for energy efficiency. So what we do here is we consider the fact that chemistry is energy intensive. Chemistry is actually linked to a huge amount of the energy consumption in the economy. So trying to make reactions more energy efficient is really important. So for instance, it can happen by designing better your reactions so that you could use things that are going to minimize the use of energy. For instance, in the steering, in the cooling, or in the heating of a reaction. Another point here is the fact that we could use renewable feedstock. So moving away from petro-based materials, which are linked, we know that, to the emission of a lot of carbon in the atmosphere that causes climate change. We could instead use the wonderful variety of molecules that biomass has to offer in order to make products. And that means that when we eliminate CO2, the CO2 is actually sequestered back into biomass as opposed to being released in the environment, as it is the case when we use petro-based chemistry. That's the reasoning. We have started to discuss a little bit about how it's not always that easy. There's some biomass that is better than others, and we can continue this discussion if you want. But in general, this principle is an important one to use renewable feedstock. Oops, sorry about this. The number 8 is use less derivatives. So that's a little bit technical to chemists here. I don't know if we have a lot of chemists in the room, but when we make chemical transformations, we typically use several steps to go to the product that we really want to do. This is particularly true in drug synthesis, because when you want to make a drug, it's usually a very complex molecule. So you need to add something here, then add something there. So there's lots of steps. So this is an example of the design of penicillin, which is a really important drug, very important antibiotic molecule that we use in our lives. And this is an example of how you can go from 1, 2, 3 steps to go from this molecule here to the penicillin product that you want. And this, you can actually replace these 3 steps by just 1 step. If instead of using pure chemistry, you turn to nature to help you and you use an enzymatic process to do this. So that's an example of how you avoid derivatives because you use less steps in the process to do that. The number 9 is called catalysis. So who's never heard the term catalysis in this room? Everybody is clear on what catalysis is? No, I see someone who's not. Okay, got you. So a catalyst is a little something you're going to add to your reaction to make your reaction function better. It will make the reaction faster, and sometimes you even allow the reaction to happen when otherwise it wouldn't happen. So usually you put a little less catalyst than you add reagents because you only need a... And the way this works is that your catalyst here will encounter the starting materials. It will make them react together to form the product, and then it will be restored so it can be reused multiple times. So typically you can add 1% of the catalyst and it will do 100 cycles. And at the end, the reaction is finished. So 1% is an example. You can go to 0.1%, 0.05%. You can have very, very active catalysts that you only need to put at ppm levels. But the principle is there. So you have lots of different types of catalysts. You could use, initially a lot were based on metals. Biocatalyst enzymes are also a form of catalyst. And now more recently, people have also developed catalysts that are void of any metal. We call them organocatalysts, and they're very powerful as well. The number 10 is design for degradation. So you remember how we discussed this fact that when we have materials that accumulate in nature, if they're toxic, it's really problematic because they will accumulate and continue to be toxic over a long period of time. Well, if you design your molecule to be degradable, meaning that nature can break it down, ideally down to complete mineralization, meaning CO2 and water, then you have a better system because it's not going to accumulate in nature. So here are examples taken from plastics. So these are some of the most classic plastics you have around you. Polyethylene, polypropylene, PVC, polyethylene terephthalate, which is, we don't have water bottles today. Oh, there's one over there. That's polyethylene terephthalate, polystyrene. If we replace them by PLA or PHAs, we're going to have materials that are much more degradable. Although PLA is not as degradable as you would want it to be. But for the sake of the argument, we'll use them as the good guys here today. So that's what you want to do. You want to design for degradability. The number 11, it's a little bit technical. It's a little bit chemical engineering as well. It's this idea of doing real-time pollution prevention. So when you're running a process, the temperature in the reaction can vary a little bit. The exact measures of the reagents will vary over time. So what you want to do if you have a big plant is to actually control parameters that are critical for the reaction so that you can stop the reaction exactly at the right moment or adjust parameters of the reaction, temperature, pressure, quantity of reagents at all times so that you optimize absolutely your process. There are some processes that work very well, have wonderful yields. But when you operate them, small variation to reaction conditions will cause big problems. So this is what you can avoid by doing this real-time analysis. And here, the analogy here is to say, okay, which piece of bread would you want? Which one would you like to have? Number 2? Okay. So what you can do is, as you are doing that, we've all been there, right? That we put the piece of bread and this is what's coming out, right? So what you can do is you can stay next to it and look at it. And then when it looks like that, you take it out. Or you can have a little sensor, I don't know, that's going to look at the color, whatever. Something that's going to look at the smell that's coming out of it, I don't know. But you have something that will pop it out right there, like what you like to have. Exactly. So that's the same idea that you can do inside a chemical reaction. And in the laboratory, there are solutions to do that. So people can use different types of sensors so that they can monitor this and have, in fact, something done completely automatically that there's a feedback loop that is going to constantly check that the reaction conditions are optimal. And finally, it's safer chemistry for accident prevention. We discussed very briefly the Bhopal incident yesterday, which remains the most deadly incident, chemical incident that has happened in our history. The idea is to really think about this process in a way to avoid this from happening altogether. So we're not going to go again into the details of what happened. Lots of measures of safety were inoperant or inactivated or ignored. But essentially, if you design your syntheses to begin with so that you don't even have methyl isocyanate for this reaction, you can avoid having this problem altogether. And this is what green chemistry is all about. So the 12th principle, should be how it's done, but it's not always how it's done. Industry is still geared towards cleaning up after waste. Scientific literature is still filled with approaches that are inefficient by design. Reagents and solvents are seldom selected with regard to hazard. Industry chemicals do not have minimal hazard as a performance criterion. Persistence of chemicals in the biosphere in our body is a major global issue, and this is really something that we see more and more of. The vast majority of organic chemicals are still made from depleting non-renewable feedstock, and our chemical industry is still largely deals with safety through engineering. But we can do better. And in fact, there are some really good examples that we've been showing you and we will continue to show you throughout this week to say there's a better future ahead, and we're already doing much better than that. So, so again, some of the ways that we're going to fix some of these issues as well is by shifting our way of thinking from a very linear idea to one where we actually go more circular. Because if we start to go circular, we have to actually integrate a lot of the principles we have out there. Would it be just the renewability? Would it be the lack of toxicity? Because we cannot continue reuse things to be toxic. So it's really helping us take out as well this component. And doing that will also require that we design our products differently. So all of this is actually coming hand in hand. What's really important to understand is that we have these 12 principles and we discussed it. But as I was going along with them, you probably realized already that many of them actually overlap. Many of them actually have talked to each other. A great example is atom economy and pollution prevention. If you do great atom economy, you're going to have low waste and you will prevent pollution from happening. If you have a safer solvents and if you design for safer chemistry, often it trickles down to having less accidents as well. So you see there are some connections and links between them. And this is why it's often hard to find examples that would fit really perfectly any one of these, because they often overlap between different one of them. When you start to act on one of them, that you start to play on many of these principles. Another thing that's really important about green chemistry, and that these 12 principles actually pointing towards, is this idea that when we have the green chemistry in place, we're starting to think outside the box. So the product or the chemical transformation that we have here is the thing that as chemists we think all the time about, or chemical engineers as well. We think about that all the time. What we need to do is to de-zoom, look at all the world around us, the interaction of this reaction with its starting materials, with the world outside, the atmosphere, the planet, the environment. So we need to actually have an approach that is more geared towards systems thinking in the world that is open, that is around us. So today, in order to solve some of these problems, we have to actually think outside the box and to think about the system as a whole. It's essential to recognize that chemistry and us, we're all the parts of a bigger system. And if we don't start to think it's systems, the good intentions that we have are going to lead to unintended negative consequences. So this idea of systems thinking starts with very simple ideas, such as you have cause-effect relationship to deal with. So for instance, if you're thirsty, what you're going to do is you're going to drink, right? And if you start to drink, you're going to become less thirsty. So this is like an interaction, very simple interaction between a system of two things. Being thirsty, and drinking. In reality, the same relation is probably linked to the cause-effect relationship, where A cause B, and then B will have a negative feedback loop to A. So when you start to take into account the toxicity and persistence and relationship between the two, you have these really interesting relationship that builds up, right? So you have a chemical, the chemical is toxic. And if it is non-persistent, meaning if it degrades, then the fact that it will degrade means that it will cause less toxicity as time evolves. So that is a positive effect. If you have a toxic compound, but it is persistent, as you have more and more accumulation of material, your toxicity is going, and eventually you end up in the system that is more toxic. So this is just to show you with very, very simple example that toxicity and persistence, which so far we've seen are two separate elements of a molecule, actually are linked. And when you think about them together, if you think about them as a system, you start to realize that there's a lot of implications about these relationships. Another way to look into this. So if you think about the CO2 in the atmosphere is the result of many things that are happening on the planet, whether this is the photosynthesis of plants, which is going to take it away, whether this is respiration of animals, which is going to add CO2 to it, whether this is combustion of fossil resources, which is also going to add to it. So this is another example of a complex systems with lots of inputs and outputs that you need to consider. So this is I guess the result of a workshop that you guys did one day. I recognized this board because I did my postdoc some 20 years ago at Yale. And this is, I recognized the chalkboard that we were using for our own group meetings. So when I saw that, I was like, oh my God, you did a workshop on that. So that was an effort to try to capture chemistry as a system, right? So thinking about raw materials, so starting materials, the manufacturing, the use phase, and the end of life, and starting to look at all the things that are going to impact green chemistry in that context. So is it during manufacturing? Is it explosive? Do you use plastic? What's the processing? Do you have byproducts? In the raw material, what's the feedstock, the sourcing, materials input? In the use phase, do you have leaching, additives? What's the time life? What's the environmental impact at the end of life, and so on? So that's an example of an exercise of systems thinking, where you look at the entire process and you start to think, oh, what are all the difficulties, the problems, the things I need to think about for my design of a material? Sorry. Yes. Another way to view this is to look at the life cycle in this sort of circular way, where we go from extraction, production, distribution, use, and recycling, hopefully, to go back here. Again, doing that is a pure example of systems thinking. It's a life cycle thinking. You think about the whole life cycle of your product. Again, a chemist will be stuck in here looking at the chemical transformation. But what we want you to do is to think about the bigger picture, what's happening before and after. We want to have a wider view. And that's a really nice reference for you if you're interested in system thinking. This is a really nice book, a really nice article about how to implement systems thinking in education, and starting to think about ways to do that, for instance, by some role-playing activities, looking at how you define the systems and how you consider the systems. This is another way actually to see the system where, for instance, you think about a process in regard to the population, in regard of government, in regard of industry. So that's another layer of the systems that you want to integrate in green chemistry and in the implementation of a more sustainable economy. So what we've been talking about so far has been this concept of green chemistry principles. But of course, all of this is a lot of discussions and a lot of words and a lot of concepts. It's not always easy to really boil them down to something that you can compare and that you can discuss in a scientific way with your peers, right? So one of the ways of doing that is to say, I want to measure actually green chemistry. I want to have a number that's going to tell me, is it green, is it not green? Right? We like to have numbers. That helps us, right? Understand where we are. And this is the notion of metrics that is super important in sustainable chemistry. It's this idea that we're going to start to measure things and calculate if we're doing better or not. That's good because you can compare. I can say my reaction is better than yours. And then you're going to say, oh, no, it's not true. Your reaction's better. And you're going to show me your numbers and I'm going to show you mine and we're going to see who wins, right? But it also means that my own reaction, I can improve it and I can compare it with past versions. So it's also an exercise that allows you to improve. So I was joking yesterday talking about metrics with some of you about the fact that I have a book in my office that is a sort of a collection of metrics, and the book is that thick. There are a huge number of metrics that have been invented. You have no idea. But of course, it's not really interesting to discuss the hundreds of metrics that exist out there. What matters is that you find a good metrics for you. And so I'm going to just present a few of them, but ones that are used quite universally and that people would refer to quite easily, including company. So for instance, mass intensity is one that's used a lot in companies, energy efficiency as well. And E factor is one that we use a lot as well in green chemistry. So let's get into it. So E factor, E stands for environmental, is a way of measuring. It's a way of measuring the waste that you produce during your process. So it's very simple. It's just the ratio between the kilogram of waste you produce for the kilogram of product. So that's a very simple concept. And what this means is that if it's really high, it's not good. You want this number to be really small. Here's some numbers about what it looks like in the context of different industries. So if you look at oil refinery, look at the E factor of the oil refinery. It's super small. And that is inversely proportional to the actual tonnage that you have. The tonnage is huge, but the E factor is small. Do you have any idea why petrochemicals are so good at having a low impact factor? A low E factor, sorry. Exactly. So they use everything that they have, right? Because they have such big volumes. They have to really make out most of it. Because if they have any waste that's produced, actually, for them, it means a lot to handle, and they prefer to try to use everything. So it means they have very limited waste in the way they operate, because it's important for them, looking at the tonnage, that they do much better. Pharmaceuticals, on the other end, they have a bad E factor. Do you know why? Actually, these numbers are really are a little older, but there are lots of improvements that pharmaceutical companies are making, but it still remains higher than what you would do for petrochemicals. Do you have any idea why? Anyone wants to guess? Purification, absolutely. So purification is one of them. You're trying to make a complex molecule, right? So you have to cut them some slack a little bit. Like they're trying to do something really complicated. So they have to have multiple steps. Each of them has purification. So lots of waste is generated. And on the other side, they're selling a product that's quite small in volume, but high in price. So they can afford to generate a bit of waste, right? For them, they don't have such a strong incentive. But again, I mean, more recently, pharmaceutical companies have been doing a good job. So I don't want to paint them as too bad either. But this is a really good thing as well to show what are the incentives that are coming from just the scale of your operation into doing a greener process. There's also another version of it, which I really, really like. It's called the F factor, F for functional. And this is an example where instead of measuring the waste, you measure here whether you fulfill your function or not, and you divide that by the kilogram of product. So you will remember the example that I showed you yesterday about the spray versus the paint, and trying to measure if the spray or the paint is better based on different parameters. Well, with this fulfilled function versus kilogram of product, what you're trying to say here is that the better my function, the less product I use to achieve the function, the better it's going to be. So this is an example where you are going to use two different products for cleaning, this time window surfaces, and you can compare the two of them. And this one that has an FA of 100 is not as good as this one that has an FA of 500. So one of the concepts behind this is that you could do something called chemical leasing, which is selling a function fulfilled by a chemical as opposed to selling the chemical itself. So you're going to go to the facility, deliver the chemical, do the stuff, and then take any waste out. And the client has nothing to, the customer has nothing to care about. It just has the function being fulfilled. This is an interesting metric, but of course it doesn't tell the full story, because if you use something more toxic or less toxic, you're not going to see it appearing in this particular metrics. But it is an interesting one to look into. PMI, that process mass intensity, that's one that you find a lot in different industries out there. So it's a really important one, I would say. It is the total mass used in a synthesis divided by the product. So it does contain about the same information as the E factor, but it's doing it in a way that I think is a little bit easier for people to see. So people tend to really do that. It accounts for the yield, the reaction, the reagent stoichiometry, you include everything, the catalyst, the solvent. So it's really, really a quite integral as a process. And there's the energy efficiency as well, which is an important engineering metrics. Most energy is used for cooling and heating, pressurizing, depressurizing, agitates, and you can calculate the energy in most cases. So in my lab, actually, we started to use very routinely a little meter that is going to measure the electricity consumption. So we can plug any of our hot plate or our mechanochemical device, and we can measure actually in real time the amount of energy that we use for anything. And we can report energy efficiency this way. And that's very useful as a way to actually have an idea about this. Finally, another really important way that we could do metrics, and we discussed this at length yesterday, it's life cycle assessment. So often what you could do is to have, for instance, the PMI, an energy efficiency metric, and LCA, so that you will cover more the engineering of the process on the one end. And then with LCA, have more global picture about the impact in terms of the environment and the health. That's a good way to operate. So that's just an example of a really famous paper where LCA is compared actually to across where several polymers are compared using LCA. It's better or where across these different outputs of LCA, acidification, carcinogenicity, ecotoxicity, eutrophication, and so on. So with that, I would like to close, and I would like to keep a lot of time for discussions, because this is an area where we want a lot of your feedback. Trying to understand how we measure things and how we know something is green is really important, obviously. So we really want to hear from you what you think, how you think about that yourself, how you design your materials and your reactions. So we want to hear from you and want to open a little discussion phase now of the.
Okay, thank you, Audrey.
Thank you
for
so
the
much.
presentation. Thank you. Oke, silakan teman-teman. Boleh tepuk tangannya dulu semua?
Thank you.
Baik, kita lanjutkan dulu ke sesi Q&A atau discussion. Boleh memberikan insight atau pandangan teman-teman tentang chemistry products yang dihasilkan mungkin dari masing-masing bidang Bapak Ibu sekalian, dan apakah sudah menerapkan is it already applied with the 12 principles of green chemistry? Mungkin ada yang mau sharing, teman-teman? Silakan. Ya, boleh Ibu. Ya, yes. Boleh sebutkan nama dan instansi.
Hello, good morning, everybody. Thank you for your presentation, Professor Audrey. Okay. My name is Reni. I'm from University affecting the health. Actually, in urban setting, when it's so we have to recycle the effect of the chemistry, as you said before. But can you explain more about the concrete example? Because I'm teaching most of my students are working in a provincial government. So when they are explained with the uh, concept more detail, or the example of the benchmark of a best practice when a city is implementing the green chemistry, I think it is beneficial for them. So they are responsible for the health policy in their area, and but it's very difficult for me, especially for the beginner, to explain them. Can you explain more details about the example of successful cities implement the non-harmful chemistry, and also the concrete example of the products in the city and how to campaign it? Because
Mhm.
I realize this is more a politics or commitment, because it's investment,
Absolutely.
it's an
Absolutely.
investment because we want to be more healthy, greeny, but it costs some money, I think, in my opinion. That's the first one. And then the second one, uh I heard about the PFAS.
Mhm.
PFAS, because I give it as an example for my students in Canada or in America. So DuPont or Teflon produce them, and it's also been here in Indonesia, many things, because the materials is on the waterproof materials, right?
Absolutely. Yeah.
And we as a human use that very much, for example, in our clothes, in jumper, or in our umbrella, I think, and we are impacted with that. Can you give us, for me, the example how to avoid them
Mm.
in the practice? Thank you very much.
Thank you so much. Lots of stuff. Thank you so much, Rani, and very nice to meet you. And I wow, a lot of questions I don't know I will be able to answer. And I also want to open the floor for other people to complete what I'm gonna say, and find, maybe you have ideas about how to do that. So one of the things that we saw here is this notion of systems, right? So we have to get we have to understand things beyond just the chemical transformation, everything around. And the city is a system, a very complex one, with chemistry being implicated at multiple levels. So in the level of chemical production that you may have in a city, or just aside a city, you have industrial environments in cities where you may have production of pollutants locally that can then affect the health of the people living in the city, the workers working in the factory. You have a lot of the green chemistry principles that we saw apply very nicely to that setup, because you could say, okay, you have to reduce your emissions, you have to reduce the pollution. Maybe you can change the process so that you don't generate that toxic waste that you're going to dump just next to a school or whatever. So you have that dimension here. To do that, I don't know. It largely depends. You're right. It's a political question. Is it of the jurisdiction of the municipality? Is it of the jurisdiction of your state? Who does this? Who makes a decision? That is a really big question. Maybe I'm not so familiar with the answer, and it largely depends as well about what you have in Indonesia, right? So you have to have certainly political will on the industrial side to promote greener chemistry on the industrial side, for sure. But in the municipality, there are many other examples of where chemistry is applied in our day-to-day life. So the municipality is going to build things and use materials to build them. They're going to clean, like employees of the municipalities are going to clean buildings, and they're going to use certain chemicals. A city will have a huge procurement facility that will buy stuff, and you can put in place regulations at the municipal level so that certain toxic compounds are banned from procurement altogether, so that you can orient the purchase of detergents and so on in a way that you will reduce exposure to chemicals. So that's one dimension. You have, I don't know, it's really big. The way another example that I'm thinking about from the city of Montreal where I live is at some point the city of Montreal banned the use of Roundup, which is a herbicide that you can apply to your gardens. You can buy it and you can spray it on plants to make them die. And it used to be freely available. I mean, I remember using it when I was a child, actually, back home in France. And later it was realized that it was carcinogenic. So the city of Montreal decided to ban the selling of that compound completely on a city. And then people who have gardens, they have to find other ways to kill the herb that they don't want to have on a whatever, right? So that's an example of a green legislation that was passed and that was enforced. And now you go into any store, you cannot buy this chemical anymore. It's not there. That's just one example, but it's just to tell you that you can have an impact via political will to this. But of course, it means that you're right. You need to be able to have the knowledge in order to do this. So I think this is the role that you can play as someone who knows about green chemistry and knows about urban planning and urban health, to say there are multiple ways with which potentially toxic chemicals enter the municipal sphere. What are there? Can you identify them? And then can you have a plan of action at the municipality to address maybe not all of them, but at least some of them, the things on which you can have an impact? All of that is going to be beneficial, right? And then you were talking about PFAS as well at the later part of your question. Thank you so much. Really great questions. So PFAS are a really big problem. This is a class of molecule that contains lots of fluorine, and the CF bond is such that it's completely non-sticky to either hydrophilic things or hydrophobic things. So it's really good when you cook, because things that are more oily, they're not going to stick to it. Things that are more like water or like full of hydroxy groups are not going to stick to it either. So that's why people develop Teflon pans. This is a pan that is covered with this material. But the problem is that if you heat it a little bit too much, then the material will decompose and start to make small little PFASs that now you can ingest, or that can go in an environment, it can go in a water. And now it's really well known that in many, many places, it's ubiquitous in the water. It's been found in our bodies, and it is associated with toxicity as well. We don't know very much the effect that it has long term. It's a low dose, so I don't think that there's a good understanding of how it will impact all of us. But it's a really complicated problem because it serves a purpose that is difficult to replace. So the non-sticky pans, now we have alternatives using, especially in organic materials, like ceramics that are really non-sticky. The issue is that they're much more expensive than what Teflon was. So that's still a tension. But there are functions such as they used a lot in North America, I don't know about here, as a foaming agent for fire extinguishers, especially for big, large-scale fires, because this material has the property to not dissolve in the water and at the same time not dissolve in the oil that is causing as well the fire. So it stays in the middle and it really lowers the temperature of the fire and it puts it down. And we don't have an alternative for this. So there's still cases where people will say, we're still going to use PFAS because we don't have an alternative. But this is really causing a big problem for all the reasons that you're saying. And again, this is an example of an unintended consequence, because people thought initially, because this molecule doesn't interact with anything, it's going to be safe for us. But obviously now we realize it's toxic. So yeah. So, but I don't know. Do you guys have other things to say about that? Because that's, yeah. Okay. I was, yes, go. So does that answer your question?
Thank you.
Thank you so much. Yeah. So we can to another question, of course.
Yeah, it is a very interesting presentation. Just remind me back 20 years ago
Mhm.
when I started in Lugano in Switzerland, doing my what we call it chemical export director. I'm actually a mechanical engineer, so
Okay.
I hate chemistry because that's not my really my part.
Okay.
I like math actually, but yeah. But I still remember the list of Mendeleev, that
Yeah.
typical.
Yeah.
And then I do a mentor for one of the startups in actually in not in Geneva, but in French part. Yeah, in Geneva, I think.
Geneva. Yeah.
Geneva,
Yeah.
yes,
It's the
yes.
French part of Switzerland. Yeah.
EPFL.
EPFL is
Yeah.
Lausanne.
Lausanne, correct.
Lausanne. Yeah.
Yes. And they're doing pretty much very disruptive ideas, making chemical is not petroleum based, but it's based on biomass based. So it's based on lignin, cellulose, that kind of things.
Yeah, the work of Jeremy Lutterbacher.
Yeah,
Yeah, it's a friend of mine. Yeah.
and I tried to bring it here.
Yeah, you should.
2020, like we
Okay.
have a accelerator program between Switzerland and Indonesia.
Okay.
But I do present in Chandrasi. And Chandrasi owner is actually one of the biggest polyethylene, polypropylene, petroleum-based,
Mhm.
and one of the richest guy in Indonesia. I'm saying is like, we are not competing. I mean, he's kind of afraid that I will going to disrupt his business because it's based on petroleum based, while I don't. I said, why you just don't make a small part of agitator or boilers, just to show you that you are going into the green tech business.
Yeah.
But it looks like very difficult. And then we pull out from here, and then we just do it everything now still in Switzerland. It's getting better and bigger now. 100 liters, 1,000, and then now big quantity. And we are even selling to one of the biggest textile producers from Germany, because they require yarns from biomass lignin base. Actually, it's not more from polypropylene or polyester based on petroleum.
Yeah.
So, but this kind of how do you call it, activity is pretty much difficult here in Indonesia, to be honest. As we just close my discussion, that actually we still have a very low technology in doing raw material for doing chemistry. Actually, it's just like formulating a synthetic thickener, for instance, based on santan gum and so on and so forth. We don't know how we do it. It's not always stable. So in based on your experience, because this is very interesting for our GDP, because you know that we are in the middle income trap, no added values on the process. We are just trading. We are importing a lot from China and India for UV absorber, synthetic thickeners, antioxidant, and so on. Because I'm selling that products, and nobody really made it here. So what will be the step that you can advise us? I mean. To be into that producers. Thank you so much.
Yeah, that's a big question. Yeah, I mean, Switzerland is one of the probably best environment to develop that, and I mean, Jeremy has a couple of really outstanding processes out there that I know has been able to scale so far, and it's really wonderful to hear that. But in Germany, in Switzerland, they have this environment where they have lots of companies around, lots of people to interact with, lots of backers, lots of subsidies from the government and also from the industry. So it is a bit of a privileged environment that in Canada, for instance, we don't have. So for us, our scale-up processes, I envy Jeremy because my scale-up processes stories are a lot more complicated and we're much more lonely than he is. So I don't know enough about Indonesia to really give you some advice, but what I think is quite interesting is that you have, biomass is a huge resource here, right? So again, we need to be very careful about the way it's handled. It needs to be done with care, but there is a space, I think, for Indonesia to develop a strong bio-based economy based on the resources that it has. And there are some interesting avenues out there for doing that. And I think, and of course, there's also some really fantastic research happening here as well to be implemented. It seems to me that there needs to be more support, especially to pass this gap that we discussed yesterday between innovation and application. So I'm not familiar enough with the environment in Indonesia to comment further. Maybe, I don't know if my fellows here wants to add to this, because they have more expertise in this. But it's a big question. Absolutely.
Yeah, maybe I think resources are, of course, extremely special here. And they're very different to the resources that economies in Europe or North America will use. So I think it would be probably the most powerful approach to see what are the wastes that you get out of your palm industry? What are the wastes that you get out of your other large-scale bio-based industries, and figure out ways on how to extract lignin from palm waste, for example. Maybe that lignin has different characteristics to lignin that's usually extracted from eucalyptus or pine trees in other parts of the world. So I think every country should analyze the flows, the waste flows that it generates from its particular geography. And maybe there's a lot of potential. Yeah.
I mean, it's a really good question, and happy to talk more. But the very good tool I've seen for that is country level material flow analyses, and you can start to see the inputs, transformations, and outputs of each country by mass volume, and you can start to identify some differentiation rather than competing directly on lower cost, high volume commodities. Start to identify perhaps higher value added products. But these global material flow analyses could be a very good start for research, especially if you have some interested students in the room who could do some research reports for you. Yeah.
Thank you for the sermons for your basics. It's very interesting, and I think on one thing that you mentioned, showed us. Sorry. You showed us this system dynamics, this system flows, and you mentioned about visual and measuring, right? So I was wondering how, to what extent, I would say, simulations. Yes, like
Yes.
simulations in this. I see it as an opportunity, actually.
Absolutely.
As consultants and seeing how things might go here and there. So
Absolutely.
simulations, like
Mm,
now I think the computational power is getting better and better in the world.
Mhm.
I think it gives us some chances to simulate things, right?
So you're absolutely right, and that's a fantastic question. Thank you so much for asking. So it is definitely an area where people are doing research, but more research is needed, obviously, and you might have some great ideas about how to accelerate that. One example I can give is the work of my friend Jakub Kostel, who has been using different digital tools to develop an understanding to predict toxicity, essentially. So one of the big issues that we have is that I mentioned earlier that in LCA, for instance, we often have gaps and holes in the databases that we have, because not the toxicity of all chemicals have been tested, and they've not been necessarily tested for all the different toxicities that you want. So now, based on the toxicities that we know, we could use different tools, including artificial intelligence, to predict the toxicity of molecules we've never made, or even molecules we made but never had the chance to test. And that really helps, accelerates, and predicts, so that we can design molecules, in fact, knowing before we even made the molecule that it might or not be toxic. So that's a really interesting guide that can help. So that's an example of exactly what you're describing in the context of understanding toxicity, for instance. And you can do that for biodegradation, as well. I don't know from the top of my head anyone doing that, but it seems a very, very obvious thing because it's very similar to toxicity in the way it works, because biodegradation is based on biological processes, right? So so it sounds like a great PhD program for one of your students. No, you're not interested? You could do that. Yeah, you should do that. I think, that's definitely something to do.
Okay, so we'll continue with the discussion. This is a question from the Zoom. So what is your opinion about the extraction or purification step of organic pollutants like POPs, PCBs, pesticides, etc.? Need green solvent, high grade or low exposure to isolate from the environment samples. So what's your opinion on extraction?
I'm not sure I fully understand the question, because do they want what is your opinion about the extraction or purification steps? So usually organic pollutants come into the environment as a result of some leakage or emission of a process. So usually, in order to avoid that, what you have to do at the process level is to making sure, for instance, that you put filters and scrubbers so that these pollutants are not ejected into the environment. But there's a lot of other mechanisms by which POPs end up in the environment. For instance, and we discussed this a little bit today, is leaching from products. So you have a Teflon pan and you overcook it a little bit, and suddenly these small PFAS now become mobile, and you eat it, or it gets into the you typically eat it actually, or you wash it and it goes into the drain. And this is how there's no real place where you can extract them. One thing that you can then think about is that, okay, they're in the water, so we're going to have a municipal water treatment. Can we extract the POPs at that point? So then POPs in the municipal water, we know, are PFASs, phthalates, these types of plasticizers we have. They are antibiotics as well that end up as well in our sewage system. It's very, very hard to extract them because they're present in such a small amount that, to my knowledge, extraction is really not the way to go. It's not going to work because there's too few of them. So what people have been using, it's more methods to try to completely oxidize the compound all the way to CO2. So there are some oxidation reactions that have been developed to do that. Other ways are by absorption. So you will put them through a filter. The filter will sort of trap them. But again, it's very hard to do at the kind of concentrations you're working on at that point.
So my opinion is maybe you have to identify, like when you're creating a product, you have to identify the problems that it can happen. Like the Teflon, like when the temperature is too high, we identify what are the possible pollutants, what are the possible extraction, right?
So this is when we talk a lot about design, indeed, is that if you design your product so that these things are not going to leach out, you're not going to have to then fish them in the environment where they're present at really low concentration, and it's very hard to concentrate them and treat them.
Mm-hmm. So the end users is process treatment or absorption. Before it's entering the environment, we filter them.
Exactly.
Right?
So you could use some filters or some columns that will have affinity for these compounds, and they can be extracted. But it's not. It's challenging to do that. There are other people. I mean, on PFAS, for instance, there's some really interesting discoveries that people are making using different types of catalysts that are degrading PFASs, even in small quantities in the water. So there was a discovery, for instance, made in British Columbia very recently, where they found a process using UV light to degrade PFASs in the water. So that's an example of what potentially in the future technologies that we could have.
I guess there is also another question. Okay.
Okay. Hi, Audrey. My name is Natasha from Pertamina Foundation, and I'm Master of Business Law student in the University of Indonesia. I'm interested about your explanation, continuing my question about greenflation and your explanation today that mentioned about new energy, renewable energy. Overall, I strongly agree that we should transform from commercial energy to green and clean energy to make a better world. And of course, for sustainability, just like trilemma energy, security, sustainability, and affordability, and also the economic we know about supply and demand theory. But if we talk about affordability in new and renewable energy, there's a lot of challenge. How can we supply if there's no, or let's say there's just a little demand in the society? How can we boost the demand in the market? Thank you.
Yeah, this is a great question. Thank you so much for that. So we started to address this point a little bit yesterday. What is difficult is that you have to go through a transition where locally it's going to cost more to go green, but in the long term, it's actually going to be cheaper. So it's how you pass this bump so that you can incentivize people to pass that period where it's going to be a bit more expensive. So again, mechanisms that can exist is so we discuss carbon tax, so pricing of the pollution imposed on the legacy process so that then this price difference is sort of lowered. You can have but that of course comes as well with a lot of challenges because it's not very politically popular. So people often are not really happy to go that way. The other route is to incentivize changing the method. So for instance, you can have there's this in many jurisdictions. I know in Europe it's very popular. In Canada, they only started to do it now, but it's this idea of the government will subsidize people for changing their technology. So for instance, they will subsidize people for retrofitting their electricity in their home, retrofitting their they will just give you money to help you change your glasses for your window pane, so that they're going to be so in Canada it's very cold, so if you have like double window panes, you're going to have less heating to do. So that's a way to reduce your consumption. So in Canada right now there's something called green building, and they will give you some tax credit if you make some renovations at home that will lower your consumption. So that's another mechanism that the government can have in order to incentivize people to change technology. They can, of course, do the same thing with companies as well to also change the practices in the economy. There's all sorts of ways that you could do subsidies to do that and to try to compensate for indeed this greenflation that happens. Again, I know if you lose money in 3 months, your board is going to be very unhappy with you and you're not going to have a good time. So it's hard to make long-term investment these days for this reason.
We have time for one more. Yeah.
Hello, thank you Prof Audrey, for your presentation. My name is Ulfa. I work as a researcher in consulting company. The name is SSC International, and actually I am still new for this topic. Is sustainability or green chemistry. In the 12 principle, one of them is safer chemical. The safer chemical designs to minimize toxicity while maintaining function. This is particularly relevant in an industry where direct human contact with the product is frequent, such as personal care and agriculture. So my question is, what are the advantages of designing safer chemicals in terms of reducing toxicity to humans and ecosystem? And how does this principle influence to product formulation, for instance, cosmetics and agriculture? Thank you.
Yeah, thank you so much. So that's a very good point. So my understanding is that in many places around the world, you have very high regulations when it comes to pharmaceutical compounds and drugs. But the minute you go to cosmetics, actually the regulations is not as stringent. So, and you have parts of the world where people have cosmetics that are really well known for being toxic. I'm thinking, for instance, about the hair products that they use in Africa, for instance, for straightening the hair, and that's really, really toxic. So I'm not sure I understand your question completely. I think that a lot of what the green chemistry principle says is that if you're designing compounds, whatever the use, you have to design them to remove toxicity. But I would say, especially if this is to be in contact with people, you have to be particularly careful. So the things ending up in toys and cosmetics, indeed in agriculture, should be really scrutinized, especially for that. But the regulations are often not very stringent on these things. So in agriculture, there are repeated examples of pesticides, herbicides that have been used that have carcinogenic activities, and the regulation has failed to protect people up to now. So what green chemistry says is that we want to do a good job, notwithstanding what the legislation is going to be. And I think that's good, but I think that you also have probably to have an incentive from the government to help you do that better. But am I answering your question, or was your question a bit different? I'm not sure I fully understand the point you wanted me to address here.
I think the second question is very clear, but the first one is, what are the advantages of designing several chemicals in terms of reducing toxicity to human and ecosystem?
Yeah, so but the advantage is obvious, is that you're going to prevent these unintended consequences in the future. So if you, from the start, have a good molecule and it's non-toxic, the molecule doing the function you want, then you're good, and you avoid risks in the future, risks that can be regulatory. So let's say if at some point the government decides to say, we ban any toxic chemical of that class to go in a cosmetic, and you're selling that particular cosmetic, you're in trouble because you have to revisit your entire formulation. If you had an inherently safer chemical to begin with, you don't have to worry about it, right? The other thing that so there's also legal implications. People can sue you, and we've seen like class actions in various jurisdictions around the world of people going after certain companies for selling toxic compounds. So you reduce the regulatory risk, the legal risk. You reduce as well consumer perception risk. If suddenly it's known that you have a toxic compound, and then all the customers decide to stop buying your product, so this is another like PR, public relations risk that you are avoiding. So these are some of the advantages that you have to be proactive and making sure that you don't put products that are toxic in your formulation to begin with.
Okay, thank you so much, Prof Audrey.
Okay, I think one more
Is
question.
there another one?
Jadi?
Yeah, you want to say something? Yeah, go ahead.
I mean, I think your question is getting at how do you make companies not pollute, right? And ultimately, I think science and activism has taken a lens of being a moral argument, and I think the moral argument is the highest ground. But in actuality, by following these green chemistry principles, you can avoid a lot of future damages. I mean, if you look at 3M and DuPont in the United States, they are now paying tens of billions of dollars in class action lawsuits to people who have been exposed to PFAS. And by actually applying these chemicals at the beginning, or these processes and these design principles at the very beginning, they can avoid that future payment. So that argument alone is likely enough to be compelling without even adding to the fact of reducing human suffering or permanent damage to the global environment. So I think it really depends on who you're talking to and who you're trying to convince of what. But if you're talking to companies, I mean, avoiding the cost of these future risks should be enough for any forward-thinking CEO or CFO to integrate these policies into their companies, which is what almost all of the large chemical manufacturers have done globally already.
Okay, thank you. It's very great discussion. And on this today discussion, I want to back to your yesterday question about the roadblock. I think the roadblock of the green chemistry is mostly about the where people will say that about the awareness of the people. But the problem is the main roadblock is the government focus. Currently, the government focus not on the environment. They do the like like doing forest conservation, but the other side is forest damage. Yeah, and others mostly about the currently the green chemistry is mostly is will be about the cost itself. Let's say like in the convenience store, they do the about the they do, let's say, the green chemistry. They cut the giving the plastic back, right? By they substitute with another. So by doing the green chemistry with the other business, they cut the plastic bag and the other side they sell the other bag, where the bag is not green chemistry also. So they doing the green chemistry by doing the other damage.
Yeah.
So like where we solve the problem with any other problem is the main roadblock, I think. And also for the option also. Okay, let's any other side. What is the goal for this green chemistry? Is I mean not the goal. Yeah, the goal is very good, but what is the government role? Yeah, what is the government role? Is there is there any new rule or new regulation to implement this green chemistry? But the other side, the industrial and also the people will be like will be scary if there any charge, any tax or others. The assumption is when we want to apply the green environment, and the government will be charged new tax. New. It should be the government better will give the incentive for the industrial or the people who will be the pioneer of doing the green the initiator of the green chemistry. So it will be good for many people, yeah, and also the industry. Then there will be try to be the pioneer of to apply this green chemistry. So the problem is don't make the green chemistry is another business. That's what I mean. What do you think?
Yeah, no, I think you're certainly nailing a lot of those things. I agree completely with you when you say that some of the ways people do it is just displacing the problem instead of really addressing the root cause of it. And we certainly want to avoid that. And then the role of government, I mean, it's depending on how cynical you are about this, it's definitely it's a big question. So look, I think that's in the end, we want to live in a society where our children are not exposed to bad chemicals, where we're going to reduce impacts on our health. We want to make sure that we can preserve our beautiful environment. So you have an incentive there to do that. The question is, how is it translated by the government into action? And also, how is it translated by the people to vote for the right person or to give good feedback to the government about that. And I think that's where your question is getting at. I don't have the answer to that question.
Yeah.
I know that a number of jurisdictions are doing that move and have seen incredible benefits from doing that. Is there resistance? Yeah, companies do resist. Sometimes even the people don't understand the link between these new regulations on the one end and the benefit to their health on the other. But you also see a lot of people being very defiant about government because they don't protect their health. And I think that we have to, I think we have to do something about this. But yeah, maybe you want to say something more.
Because that I think currently the government waiting the problem first, then
Yes, and then
Then
addressing
make the
it.
rule.
Yeah,
it
not
should be
proactive.
the regulation first, regulator first to prevent the problems. That the things.
Maybe the word is science evidence-based regulation. So yeah, when
Yes.
conducting the regulation, it should be science evidence-based. Yeah. Because with that is the fundamental. We know the outcomes, and also the from the business side, it should be economic, right? Yeah. So that I think that's the. I think we can summarize that. Would that be okay? Yeah. Okay. So I'm sorry to cut the this interesting discussion because it's break time, guys. So it's we're supposed to have, yes. No, 5 minutes. It's okay.